the talk is about transactions, which are familiar to everyone, I hope, from database theory. When we talk about transactions in memory models, we're typically talking about using them in order to replace locks. And this area is actually very well studied. The one thing everybody agrees on is the basic notion of a transaction. It's an atomic event. It happens all or nothing. After that, it gets a bit messy. So, for example, what order should the transactions be seen in? The standard answer is serializability. What that says is that there exists a total order that explains all of the transactions that have committed. But there are stronger notions, for example, some that enforce real time, and weaker notions, which, for example, allow a partial order. The status of aborteds is also something we can debate. For example, if you read something from an aborted transaction, can you use the value that you read in another transaction? If you allow that, you end up with something called opacity. And if you don't, you end up with weaker conditions, which are slightly less clear. There's also the status of non-transactional code. If we force atomicity between non-transactional and transactional code, we have something called strong isolation, but there are also weaker notions. So this is just to sort of give you the lay of the land of all the things that we know about transactional memory. And what we'd like to do is simply ask all of these questions once again, but this time while we're relaxed. So the one thing that's non-negotiable here is atomicity. But what about order? And the key idea that we had is that memory models are full of order. That's what they do. And so why not use it? So if we use that order, what we get is causality for free because those orders are causal. We in general do not get real time because those orders do not enforce real time. And in fact, we in general don't get even standard serializability precisely because these orders don't necessarily give you a total order on the transactions. It's in general just a partial order. So one of the things we are interested in is in what circumstances could we get a total order? And it turns out that that happens sort of for free for models such as those will be discussed in the next talk, which are have a global happens before or are multi-copy atomic. I'll call them GHB models. And in that case, we actually get this kind of nice total order. For aborteds, what happens is that doing nothing, just doing what we think we're doing, we naturally just get opacity. So doing a little bit more work, we can come up with these weaker notions, but it is more work. And for non-transactional code, we very, very naturally get isolated transactions. To get relaxation just requires a tiny bit of work. So, all right, so the basis for our work is the framework of Alglave, Meringer, and Tauschnig, which we'll call AMT. And the basic idea there is we have some events. Those are labeled with actions like reads and writes. And we have some orders over those actions. So many of these are program generated, such as program order and various dependencies. Others of these arise by resolving non-determinism. So for example, if I have a read racing with a write, one thing that could happen is that the read could see the write. The other thing is that it might not. And so we get either a dependency or an anti-dependency in one case or the other. When we resolve two racing writes, we get something called coherence. And what we do is, the basic idea of the AMT machinery is you feed all of these orders into a machine, and it pops out a bunch of additional orders, and some of these, for example, are called preserved program order. The machine tells you what order it wants to preserve in program order. And then what we look for then is various sort of acyclicities. So that's the basic idea. So here's just an example. And this is the famous load buffering example. So there's code on the left, but the semantics on the right. So what I have is a thread that's writing X and then reading Y, and then another thread which is writing Y, then reading X. And so the question is, can you write X and then read 0 in one thread and write Y and then read 0 for X in the other thread? This is disallowed under sequential consistency because we have an evidence cycle here. violating the program order versus from read. However, under TSO, this is perfectly fine because TSO relaxes the program order between writes and reads. So if you want to disallow this in TSO, you need to introduce fences. So let's take that example and recall that this is an allowed example under TSO. And let's just make it atomic. So what happens? So what I'm going to do in the picture here is just show the atomic transactions as little boxes. And the essential idea we had is, well, let's just lift all of the relations that are there from relations on the individual events of the transaction. So if, for example, there's a from read relationship to one event in the transaction, then we'll give the from read to every event in the transaction. So that's the idea of lifting. And then we just look for acyclicity. And in fact, that's sufficient to prevent this particular execution. In fact, there's some wonderful consequences of just doing this. So because AMT validity implies acyclicity, we get a partial order. Therefore, we get some kind of causal serializability. Because the model ignores real time, we are ignoring real time. Real time is a bugbear for many, many transactional models. They get all tripped up in real time. So we're not doing that. And in addition, empty transactions or single events as transactions, the transactional code can be removed. It's obvious because all we've done is lift. So, and because we've lifted not only the transactional events, but note that the lift includes the non-transactional events. Oh, there we go. Such as the initialization here, which I've just written as a non-transactional event. And therefore, we automatically get strong isolation because in order to avoid acyclicity, this guy has to be ordered with respect to every event of that transaction. So strong isolation for free. OK, so that's the basic idea. And I could more or less stop the talk now, and you could all figure the rest out. But let me just go ahead and tell you what we did. So some things we want to deal with here are nested transactions. We also want to deal with weak isolation. So here's an example that distinguishes this where the read is seeing an intermediate state of the transaction, which is not allowed under strong isolation. And we also want to talk about various abort models. And this is a little bit more complicated, so I'll come back to this example. All right. The basic definition is that we're going to say that an execution with transactions is correct if it's valid under the AMT axioms, assuming some lifted relations. So we're going to lift this relation O between E and D, where E is a transactional event. Well, actually, first of all, if E and D are related in the underlying relation, they're related in the lifted one. Otherwise, let's suppose E is a transactional event. Well, then we're going to relate E to D whenever there's some E prime in the same transaction, and D is not in that transaction. All right, that's it. So that gives us all of the goodies we had on the previous slide. To get nested transactions, all we have to do is be a little bit more generous in our notion of what it means to be in the same transaction, put a little hierarchy in there, and that solves that. What we have here, as I said, is strong isolation. If we want weak isolation, then we need to put some caveats in here. So we don't want to lift transactional events that are in weakly isolated transactions, unless, of course, we're relating them to another transactional event, okay? In which case, they need to be ordered. All right? So that gives you weak isolation. And for the abort model, what we really need to do is just to put an extra condition in here to say that there's some restriction on what you can see from an aborted transaction. In general, there's different choices one can make here. What we've chosen to formalize is that if you have an aborted write, it can only be seen, for example, in another aborted transaction. Okay? Generalizing that just slightly, we say that we don't also want aborted reads to affect any other transaction except for an aborted transaction. This gets a little bit tricky because detecting control flow. For example, if there are registers set in aborted transactions, and sometimes those leak out. So we've sort of defined this, if you like, parametrically with respect to some notion of causality, which we expect includes direct reads and writes, but may not necessarily include control dependencies. And then the consequences, as I said before, from this definition, you get causal serializability, there's no real-time order, all this goodness and wonderfulness, okay? All right, so what about standard serializability? So this doesn't give you standard serializability, and I'd like to show you a standard example to demonstrate that. So this is the well-known IRIW example. So here, after initialization, we have a thread writing X is 1, another different thread writing Y is 1, and now we have two reader threads, and they read X and Y in different orders. The question is, can you read the new value and then see the stale value in each thread? This is disallowed under multi-copy atomic architectures, such as TSO and ARMv8. But this is allowed under architectures that allow writes to propagate to different processors in different orders, such as ARM7. And so we just throw transactions on there, and this is allowed by our model as well, although this is not serializable in a way that respects causality. So we don't get standard serializability here. However, we will get standard serializability for multi-copy atomic models. Now let's look at the issue of aborted actions. So here is an example where this is a forbidden execution. Right? So I have the top transaction reads X is 0 from the initial transaction. That's before this write that X is 2, which is read by the third transaction. The third transaction subsequently reads the initial value of Y, which of course must happen before this write of Y. So we have a cycle here, and this execution is disallowed. But what if the bottom transaction aborts? Is this okay? Discuss. So under opacity, this is not okay. And it's not okay because it's required under opacity that the aborted transactions must somehow fit into the order created by all of the committed transactions. And there is no acyclic order that will allow these. But this is allowed under weaker conditions, such as virtual world consistency, and possibly under TMS1. TMS1 has a lot of real-time nonsense in it, so I can't quite talk about whether this would be allowed by TMS1 because this is too abstract. But it'd be allowed under certain circumstances. So the solution we have is to check the system in phases. So what we'll do here is first we'll check the committeds and the opaques together. And we'll make sure that we satisfy all the ANTA cyclicity requirements there. Then we'll add in the non-opaque aborted transactions one at a time and check them for acyclicity with respect to their causal history. What this gives you is something very, very close to virtual world consistency. And this gives a sort of nice formal footing for these kind of conditions. Okay, oh my God, I'm talking so fast. I'm like, okay, I'm gonna have like 15 minutes left. Sorry. Okay, I'll start telling jokes now. Now, in the paper, we have a comparison of VWC and TMS1, and that goes into some detail. There's also in the paper an automaton to check violations of the global happens before order. And these are used in this proof that when we lift things up, that gives you a total order on transactions. This has all been formalized in Memaloy. What we did is we formalized these models individually. So we formalized the TSO model, the power model, and the ARMv8 model. Using non-opaque aborts. And we compared to hardware models in Memaloy for small model sizes, because that's all the tool could tolerate. And one thing that immediately popped up is that our model of dealing with aborts is slightly different from that in the hardware. And in particular, we allow a write in an aborted transaction to be seen by another aborted transaction. And that's something in general that these hardware models don't allow. So this makes us actually incomparable because there are things that the hardware allow that we won't, and then vice versa, because these aborted transactions for us are visible and therefore can get in the way, if you like, of things that they can see. So this is all around aborted transactions. But otherwise, the model we have is strictly more expressive than the hardware models. So the differences that we noted were around coherence and fences. So if you notice, we're not actually requiring fences on either side of a transaction. So whereas most of these hardware models actually do fence both at the beginning and at the end of a transaction in order to create memory barriers. So because we're not doing that, we allow transactions like this where the hardware won't. And in addition, the hardware places fences. In addition, the hardware enforces coherence with respect to aborted writes. So again, some little subtleties with respect to aborts, whereas we don't enforce coherence with aborted writes. So the entirety of this work could be seen as a way of, what we've done here is fleshed out this paper by Grossman, Manson, and Pugh from 2006, where they sort of first looked at these kind of thoughts around what a transactional model looks like. This was worked out in some detail for the data race free case by D'Alessandro, Scott, and Spear. And what we've handled is, if you like, the full general racy case for an axiomatic model like Algolov. In fact, the Algolov work has been, of course, very influential here, as has the work on mem-alloy. So we've worked quite closely in this paper with Chong, Sorensen, and Wickerson, who were developing a semantics of transactions specifically for these hardware models and provided us their models for comparison. So that's where we got those. So what we hope to have contributed here is a very high-level view of a lot of detailed grunge. And I hope I did that. And like I said, I talked really fast. So I'm free. I know I got too much time. What am I going to do? Say what? I'm only 2 minutes ahead? Okay, good. It took forever in my room.
I see no online questions, so people in the room, please.
Does your model include an implementation strategy on top of other models?
Excellent question. No. So this is definitely not, we're not doing implementation. So it's very, very semantic here. We're just looking at what kind of properties you might have and what you could prove out of them. So we're really interested in what cases you get sort of these nice abstraction results. So really, from the programmer's point of view, you want to have transactions be in a serial order, right? In a total order. So we're curious, when could we get such a total order and therefore have sort of a programmer abstraction when we just use the underlying model? So, but we don't have hardware. Yeah.
So presumably most programmers would prefer sequential consistency except for performance concerns. If you haven't shown an implementation, how do we know there will be high performance realizations of this idea? I don't, I suppose. So this is,
yeah, I'm definitely not a hardware person. So the question, so you have relaxed models, yeah? Relaxed models, people, as you heard in the previous talk, programming with locks, hard, bad. So people are thinking, well, maybe transactions will work. So what we're trying to do is provide some sort of formal footing for what that would look like. Yeah. So actually, no, I can't tell you that, oh, this is going to be an awesome performer relative to some other implementation. Yeah.
May I ask a quick follow-up?
Yeah.
Do you think if you wanted to implement it, it would be trivial how to?
Say it again?
If you wanted to implement this, is it trivial how to do that? Because
no, it's certainly not trivial. So, everything we've done ignores real-time completely. And that complicates, if you want to implement it in its full generality, good luck, I have no idea. Because all of these axiomatic models are post hoc. You run the thing, and afterwards God looks at it and says, yeah, that was fine. And that's sort of what we're doing here as well.
So at the beginning of the talk, you were talking about this real-time model for
Yes.
the sequential consistent model.
Yes.
And then you said in order to do the relaxed one, the real-time basically have to be discarded, or you don't know.
No, I wouldn't say it has to be, but it's actually, if you think of relaxed memory models as little distributed systems, it's quite natural to ignore real time.
Okay. So I guess, yeah, my question was just, are there any work on how to enforce some form of real time?
All of it.
All of
Sorry. Yeah, all the work on hardware transactional memory is obsessed with real time.
Okay.
Yeah, so this is unusual.
So that's an open problem, or what?
No, I don't. Sorry.
So, yeah.
Okay, so for example, so if you're interested in this, there's a really nice paper by Mark Moyer and other people on TMS1.
Okay.
It's very, very interesting. So what they're trying to do is they're trying to say, okay, opacity is a little too strong, and it makes too many requirements of hardware. So I'm not a hardware person, so I just believe them. And so therefore, they want a slightly weaker condition. So the weaker condition they come up with is actually really complicated because it's expressed in terms of traces with commits at certain points and what's happened at this time and so on and so forth. The condition we have, I just gave you, which I can explain to a child, implies TMS1. It's a strictly weaker, okay? And so in that sense, I think it's a win if you're interested in properties of transactional programs, not implementations.
And what TMS1 represents?
TMS1, I don't even know what it stands for. Do you know what it stands for? Transactional Memory Specification 1. And they have 2 in the paper too. Yeah.
So it seems like one of the things you're doing in this paper is taking an existing model and then kind of retrofitting some extra kind of stuff onto it.
That's exactly what we're doing.
So what I was curious about was, does this kind of point towards some rules about what sort of stuff it's okay to kind of attach to models?
Yes, I claim that it is. And in fact, what we're doing right now is doing this to Java. So yeah, it does give you a nice way of thinking about what all of these various, laundry list of knobs you can twist for transactions and which ones you want and how to work that into your model. Yes, I claim this will tell you how to do it. Yeah.
So if someone came along and said, "Hey, I've got this other crazy consistency, transaction model," that you'd now be better positioned to kind of add that, or sort of add 2 different transactions.
Oh, sorry, I misunderstood the question. I thought you were talking about a different memory model. So this is you can slap this onto any memory model you like. That I'm going to claim, including operational ones, et cetera. So it's not clear. It's not clear that we would handle other other than the things we've talked about transactional models, I don't know that we would be able to help you with that. So one thing is, I do think that the notion we have of correctness is about as weak as you could reasonably expect. So I would be surprised if you came up with something that people would say, that's okay, that didn't pass our model.
Okay, thanks.
So in that sense, it'd be a bound, if you like, on what's reasonable.
No more questions?
I am not exactly understood what is your objective. So let us explain what I understood. You have the original model.
Yeah.
Then you decide that something is a transaction, you put that in read.
Yeah.
For me, this should eliminate behavior.
It should eliminate what?
It should eliminate behavior. That is, it should eliminate the role. Behavior.
Oh, the behavior. Yes, it does. That's exactly right. It eliminates, yeah.
That's true. That's for me the strange. My explanation of that sum might be that when you have abort, it introduces new behavior that were then not really existing.
Sorry. Abort, you're right. So aborts are different. So when I say it only does things that's for committed transactions. So committed singleton transactions can just be erased. You're right. That's not true for aborts. Aborts are different. Yeah. Yeah, aborts may add new things. Sure. Yes.
So our